Okay, sorry about all the problems here with the videos, but this should be working now. There is a difference between 27 and 28 and the other logarithmic equations that we solved on page 3. The difference here between 27 and 28 is that they have multiple logarithms in the equation. 27 has 3 logarithms. 28 has 2. So these are solved a little bit differently. And even with that, 27 is a different type of multiple logarithm equation than 28. See, 27 has logarithms on both sides of the equation, which makes it different from 28. 28 only has logarithms on one side here. So I'm actually going to do 28 first because it's solved more similar to what we just did on problem 25 and 26. So the first thing we need to do is combine these two logarithm expressions into one logarithm. We have to check that they have the same base, which they do. So since there's a plus sign between the two logarithms, this is an example of the product property. So we can combine those two logarithms into the log base 9, and now the 5 has to form a product with x plus 10, so this is 5 times x plus 10, and that equals 2. Now we have a single logarithm on one side of this equation, which is more like question 25 and 26 of the review. What we did on those problems is the same thing we're going to do on this problem. We have to write the logarithmic equation in exponential form with a base of 9 squared. Now I'm going to distribute the 5 here. This is going to become 5x plus 50. Now we're solving for x, so if we subtract 50, 9 squared is 81, subtract 50 is 31. If we divide both sides by 5, we get x equals 31 over 5. And 27 is going to be solved a slightly different way. We first need to combine these two logarithms into one logarithm, and we can do that since they have the same base, and there's a plus sign between them, meaning we're going to use the product property. So this is going to be, if we combine those, this is going to be the log base 5 of x times x plus 6, and that equals the log base 5 of 55. But now this is a logarithm on both sides of the equal sign. Now since these have the same base, log base 5, and this is a log base 5 over here, these are the same logarithm, okay, log base 5, log base 5. The equal sign means that these two sides have to be exactly the same thing. Now if these two sides are exactly the same thing, since they have the same logarithm, that means that's what's inside the logarithm. Here we have this inside the logarithm. Over here we have 55 inside of the logarithm. If these two sides, the left side and the right side, equal each other, that means what's inside the logarithms also must equal each other. So if we distribute the x, we can say that x squared plus 6x has to equal 55. Otherwise, it wouldn't make sense for these two logarithms to be the same. That's what equal sign means, is to be the same. So this is just a quadratic equation that we can solve by factoring. Subtract 55 to the other side, and we get x squared plus 6x minus 55 equals 0. Now if we factor, we get x plus 11 and x minus 5, which gives us two potential solutions here. X equals negative 11 and x equals positive 5. Now this is something that's important about logarithms. Logarithm functions have a restricted domain. You can only take the logarithm of positive values, anything greater than 0. You cannot take the logarithm of negative values. So if we were to test, for example, this negative 11 in for this x or for this x, either one, it would turn out that we would be taking the logarithm of a negative number, which you can't do. It's not in the domain. So x equals negative 11 is what's called an extraneous solution. The only solution that works in this equation is x equals 5. Now the last four here, 29, 30, 31, and 32, these are all examples of exponential equations. They're solved a similar way to logarithm equations. In logarithm equations, we isolated the logarithmic term, we rewrote it in exponential form, and then solved for x. Here, we're going to isolate the exponential term, then rewrite it in logarithmic form, and then solve for x. The exponential term is the exponent with the base. That's the exponential term. So our first task on all of these is to make sure that that is isolated. Now in 29, the base and the exponent are already isolated. So our next task is to rewrite this in logarithmic form. In logarithmic form, this is the log base 8 of 35 equals x. Well, since x is already by itself here on the right side, we're done. X has been solved for. The answer is x equals the log base 8 of 35. Here, number 30, though, the base and the exponent is 2 to the x power. This is the exponential term right here, 2 to the x. The 3 is not part of the exponential term. It's a multiplying the exponential term. So we need to undo the multiplication with division. So we have 2 to the x equals 9. If we rewrite this in logarithmic form, log base 2 of 9 is equal to x. And that gives us the solution there. Now here in 31, the exponential term is the base is e, and the exponent is n minus 10. So here's the exponential term. So we have to get rid of the minus 8. We do that by adding 8. So we have e to the n minus 10 equals 30. Now we rewrite this in logarithmic form. The logarithm that we have to use, since this is a base of e, is a natural log. So the natural log of 30 equals n minus 10. But we're trying to get n by itself. Right now it's being subtracted by 10, so we need to add 10. And this is important to understand. You cannot add 10 to the 30. The 30 is inside of the function, the natural logarithm function. It's like being inside of a square root or any other type of function. The 30, it's going to stay 30. We have to add the 10 outside of the function. So our final answer is n equals the natural log of 30. And if you want to put parentheses around it, you can. You don't have to, but that just shows that 30 is inside the function, and the plus 10 is outside of it. This is not the same thing as the natural log of 40. So here's our answer there. Okay, now in 32, this is the base, this is the exponent. So this 8 right here is a coefficient, it's multiplying. So we need to divide by 8, and we get 8 to the x plus 3 equals 3. Now the base and the exponent have been isolated. So we rewrite this in logarithmic form. Log base 8 of 3 is equal to x plus 3. Now we subtract 3, and again, we cannot take 3 from 3 because this 3 right here is inside of the logarithm function. So the 3 that we're subtracting needs to be subtracted outside of the function. Our final answer is going to be x equals the log base 8 of 3 minus 3.